Dear friends and members of the KITION Planetarium Observatory, welcome to another Science Cafe, as we usually do every last Tuesday of every month. This month we have a special guest all the way from Romania. It's Andrea Boldureanu, and she was going to talk to us about the history of our solar system, of the universe, and the formation of our solar system. And after that, we're going to talk to you about the news, what you should expect from us and globally during the Global Astronomy Month. KITION Planetarium Observatory is the national coordinator for the Global Astronomy Month in Cyprus as representatives of the Astronomers Without Borders, and we will tell you what you should expect this month, what events we're going to hold, and so on. So with us tonight, as I mentioned earlier, we have all the way from Romania, Andrea. Andrea is a student at the moment. She's studying mathematics and computer science at the National College in Romania. She's interested in astronomy and astrophysics, and she also attended the astronomy and astrophysics camp in Martin Dacian Bica National Astronomy Club, and she attended it twice, actually, 2019 and 2020. And she also was a volunteer in January 2024, where she taught there for 8 hours, and she also taught about her papers and so on. She achieved, she made her own scientific publication related to astronomy, the Astronomy Journal Perseus. She published an article related to stellar evolution, and she also participated in the European Researchers' Night, talking to them about the history of the universe, as she's going to talk to us about tonight. One of her greatest achievements was in 2022, where she achieved a gold medal at the International Astronomy, Astrophysics, and Space Olympiad for juniors. And in 2023, she qualified for the national senior team for the 2023 International Olympiad of Astronomy and Astrophysics. And she was also awarded a bronze medal by the Romanian Physics Society, and so on. So you can see everything in detail about her CV on our website. And I want to also point out that she's one of the founders of the Leo Alpha Club, Libra Yashi. This club has to do with volunteering, and she's doing charity. And I also want to congratulate her, because except that she's a good scientist, as everything shows, she's a very nice person, and she's helping the society and also investing in culture. So congratulations, Andrea. So we have some honored guests with us tonight, and we have also my friend Bapotas Yannis. He's a nuclear astrophysicist. He's in international projects, and I also officially want to welcome you, Yannis. Thank you for attending. And one of our sponsors, Chris Magovic. Thank you very much. Andrea, you may share your presentation, and feel free, the stage is yours. We are looking forward to hear your presentation, and after the end of your presentation, the audience will ask some questions that you may answer. Thank you very much.
Thank you very much for the kind words. Okay, I will share the presentation. Please tell me if you can see it clearly.
Yes, of course.
Okay, so today, as you probably saw already on the title of the event, we will talk a bit about the history of the universe, and pretty much from the start of the universe, the Big Bang Theory, and then the formation of our solar system and our Milky Way galaxy, where we probably are in the universe, where is our location in the universe, and then at the end, a few theories regarding how our universe will most likely end. And obviously, what determines all of these theories? So how can we determine the fate of the universe, essentially? My name is Andrea Boldureanu, and I'm a 10th grade student at Iași National College and a member of the Iași Astro Club from Romania. And today we will talk a bit about the history of the universe. Also, I would like to say that if you have any questions or perhaps any things that you perhaps want to say, you can say them during the presentation, or you can keep them until the end, where I would really enjoy if we can have a little bit of a debate, and perhaps you can tell me what is your favorite theory about the end of the universe, and we can perhaps have a little bit of a debate on this subject. So personally, I'm passionate about history, apart from astronomy and astrophysics, and I'd like to talk a little bit about the history of the universe, because understanding the people that worked to get these theories is probably going to give us a better understanding on the theories themselves. So first off, we must understand that during the history, people ask these sort of three questions. First off, did the universe have a beginning or not? Is the universe static or in a state of expansion? And third off, is the universe finite or infinite? These three questions have been asked by both philosophers and astrophysicists and even cosmologists recently, ever since the time of Greek antiquity and of ancient Greeks. Aristotle, for example, said that the human race and the world existed and will exist forever. So they did not agree the idea of a creation. Then, after the ancient Greeks had this sort of questions, which, as you can see, was first off thought by philosophers and then by astrophysicists and physicists, we go into the medieval times. During the medieval times, we had many prominent astronomers. For example, Nicolaus Copernicus, Johannes Kepler, you probably heard of them. And even Kepler actually had a paper on the fate of the universe, and he said that we must live in a finite universe. And so this was his opinion, that the universe is finite. But then Newton's theory of gravity in the 18th century in the 17th to 18th century, showed clearly that the universe cannot be static or finite. So I'd like to ask you, what is your opinion on that? Why do you think that Newton's theory of gravity and of gravitational attraction clearly showed us that we must be living in an infinite universe? If anyone would like to answer or perhaps show their opinion, it would be great if you would want to speak on this. Okay, I guess we can talk more at the end of the presentation, but the reason why is because Newton's theory of relativity actually showed us that if the universe were to be finite, then we would have a preferred direction of attraction. So there would be one single point in space where every sort of matter would start to attract. So everything would fall into one point because of gravitational attraction, obviously if given sufficient time. But the thing is, in an infinite universe, we can see each point as an individual center. And if we see each point as an individual center, then we obviously do not have a preferred direction for gravitational attraction. So everything is symmetric. So this is the reason why Newton's theory showed us that the universe must be infinite. So after the 17th century, we knew this for sure. Our universe must be infinite. Then, during the 18th century, came the Age of Enlightenment, which brought some very prominent philosophers that actually thought about this question concerning the universe. The first one was Immanuel Kant, which is a very famous German philosopher. In his work from 1781, Kritik der reinen Vernunft, or Critique of Pure Reason, tackled this question about the universe's beginning, if the universe had or did not have a beginning. He stated these two questions, these two contradictions. He called them his first antinomies. An antinomy is basically a thing that cannot two arguments that contradict themselves. So he asked the question, okay, did the universe have or did not have a beginning? And he felt like there were equal arguments to both of them. He felt like the universe could and could not have a beginning at the same time, which in his opinion did not make any sense. So he called this an antinomy, a contradiction, because he felt like there were equal arguments for the thesis and the antithesis. I'm going to read you his two arguments, and then we can talk a bit about his flaw, the flaw in his logic, and why it did not make any sense. What was the problem behind his arguments? So he first stated that if the universe did not have a beginning, then there would have existed an infinite amount of time before any event, which in his opinion was absurd. If the universe did have a beginning, then there would have existed an infinite period of time before it. The question asked by Kant being, then why would it start at a specific moment in time? So I would like to draw a little bit of a diagram. So if the universe had a beginning, so this is the Big Bang, for example, then there would have existed an infinite amount of time before any event. So the time would be infinite before the event, which in his opinion did not really make any sense. But if the universe did have a beginning, so the universe did not have a beginning, so any event would have an infinite amount of time before it. But if the universe had a beginning, then there would have existed an infinite amount of time before it, which in his opinion did not really make any sense. These things contradicted. So the flaw in his logic was basically that he started from the idea that time existed forever, that time was a property that was independent of space, of time, of matter, which we will see in a few minutes that that is not the case. That is not true right now. Actually, in our current understanding of the universe, we cannot talk about time before the universe. The time formed with the universe at the same time. The time formed alongside Big Bang. So this was the flaw in his logic. He should have stated that time was formed when the universe was formed. Now, as we got to the 20th century, we obviously had many prominent physicists and astrophysicists. I can only name a few names that are very famous, like Albert Einstein, Max Planck, Niels Bohr. And in these two pictures right now, we have the two people credited for the current model of the expansion and the birth of the universe. You must understand that the first person that actually came up with the theory called Big Bang, that is obviously the most famous one for how the universe was formed, is the person on the left, Georges Lemaitre, who was a Belgian Catholic priest and physicist. And in his work from 1927, he started from the theory of relativity, and he proposed the model of expansion. He calculated the Hubble constant, that bears the name of the second guy right here, and he derived Hubble's law. In 1939, he called his theory the hypothesis of the primeval atom. So he should be credited for the model of the expansion of the universe, or more specifically for the model of the Big Bang theory. But the guy on the left, Edwin Hubble, who was an American physicist, actually came up with observational data that showed clearly that, okay, the universe is expanding. So he calculated with a much great precision the Hubble constant, and he stated Hubble's law, basically that the velocity is directly proportional to distance. So the further away from us an object is, its velocity that it moves away from us, it's going to be greater. And because of this, they are both credited with the current model of the expansion of the universe and the Big Bang theory. Though Georges Lemaitre was the first one to theoretically derive it, Edwin Hubble came up with the experimental data. Now, enough with history and the whole background of the history of the universe. We will go right now on the beginnings of the universe. So how was the universe formed? As you all are probably very familiar with, the universe formed with a Big Bang. And the Big Bang theory is the currently most appreciated and accepted theory regarding the beginnings of the universe. There is also experimental data that shows that, okay, it might be true, like the CMB, the cosmic microwave background, for example. And as a little definition, the universe began as a point, a singularity, with an extreme temperature and an infinite density. After it exploded, which is not a correct term, it's probably a lot more complicated by that, but it's a good approximation, I guess. Matter, energy, space, and time, as I said before, formed. So we cannot really talk about time, or actually we cannot talk about anything before the Big Bang in terms of matter, energy, or space. whatever. This is a small little diagram of the, I guess, the time scale of the universe and what happened in the universe in these 13.77 billion years. So the universe is approximately 13.7 or 13.8 billion years old. Now this is when it sort of began to form, and then we had an epoch of inflation, an afterglow light pattern, dark ages, and we are currently in the dark energy accelerated expansion because our universe is expanding, but we're not sure why, so we're blaming it on the dark energy. We'll go into detail about every period that came after it. And yeah, I'd also like to add that during the Big Bang, so in the start of the universe, is surrounded in very many mysteries, in many mysteries. For example, quantum fluctuations has said to take place that could have formed what are called cosmic strings right now, and other, I guess, sort of weird cosmological effects that people have theorized. So this is where, if you heard about the cosmic string theory, have I guess emerged from. After the Big Bang, we must understand that we can divide the timescale of the universe into two main eras. First off, the radiation era, which spanned approximately 50,000 years, and then the matter era, which spans until today. The radiation era can be subdivided into 7 or in some instances 8 epochs. For example, after the Big Bang, we first had the Planck epoch, the grand unification epoch, inflation, electroweak, quark, hadron, lepton, and sometimes a nuclear epoch as well. In the next one, the matter era, we can only divide it in 3 main epochs, but we'll go into that later. I'd also like to add that we will not go into much detail into these epochs, but we will talk a bit about the most significant things that happened during them. So this is basically a diagram of the Big Bang and then the time after it. You can also know that the temperature decreased exponentially. So from 10 to the 40th kelvins in the start of the I guess in the first few, not even seconds of the universe, and we got all the way to 10 to the 9 power kelvins. And today you can see that we are only at 3 Kelvin, the mean temperature of the universe. So yeah, the universe was very, very hot when it first formed. The first epoch is the Planck epoch. Now, in this Planck epoch, in my opinion, it's definitely the most interesting. You probably heard about it. It's very famous, and it has many things named after it. You can also have here the Planck temperature, something called the Planck length, or even the Planck time or Planck period. What is so interesting about this Planck period is that we do not know anything about it, like nothing. The only thing that physicists know is that all 4 fundamental forces that we know today, like the gravitational force, the electromagnetic force, the strong nuclear force, and the weak nuclear force, were united into one fundamental force, also called superforce. And all that we know is that there wasn't any matter, there was just energy in the universe, and that after this time, called the Planck time, as I stated before, the gravity basically detached, separated from the other 3 forces. And some physicists say that the theory of quantum gravity, actually the secret in the theory of quantum gravity lies inside this Planck time. So you know that currently we need to bridge the theory of relativity and the theory of quantum mechanics. And to do that, some people say that the secret might be in this Planck period, because we currently do not have any physics models that can accurately describe what happened in this Planck time. We can only sort of use our classical model, not just classical models, all models that do not really work that well. So we need to implement and find what is called quantum gravity. This is why the string theory actually came to be, a sort of a response to quantum gravity, but it's not perhaps the best method that we currently have. Then after the Planck epoch, we have the grand unification epoch. And the most interesting thing about this is that all 3 fundamental forces were united as one, and this era ended when this epoch ended when a strong nuclear force separated from the rest. Then we got onto the inflation epoch, which just had a very quick inflation of the universe. Like in just a moment, the universe went from microscopic scales, from like the size of an atom, up until macroscopic levels, like until the size of a grapefruit. So this is the inflation era. definitely very significant. Then the electroweak era, in which the weak nuclear force and the electromagnetic force separated at the end of it. And now we're on to the last three epochs, which are very interesting because they are sort of paving the way for what is called nucleosynthesis. In the quark era, obviously quarks were formed. In this hadron era, protons and neutrons were formed. So we have like elementary particles. Here we just had elementary particles. Now we're on to subatomic particles. Protons and neutrons are a type of hadron. And in the last epoch, we are talking about leptons, which are electrons. So now, okay, we have protons, neutrons, and electrons. The universe is cool enough for matter to start forming, so we can start what is called nucleosynthesis. Nucleosynthesis means that protons, neutrons, and electrons can bind together to form atoms. So now that we have atoms, we finally have matter. We have hydrogen and helium atoms for now. Now that we have matter, we can start going away from radiation era into the matter era that spans until today. So in this atomic epoch, as I said, at the start of this atomic epoch, we just had helium and hydrogen. We could not really have like heavier elements. Then after this atomic epoch ended, which was basically when more and more atoms and more matter started to form, we're going into the galactic epoch and then into the stellar epoch. Now we might see something weird. Okay, but like, how were galaxies formed before stars? Now, this is interesting because we have to understand that when we are talking about the galactic epoch, we're not talking about like actual galaxies. We're talking about more like proto-galaxies. And these proto-galaxies were like more like clouds. And inside these clouds, molecular clouds, stars could be formed after, nuclear fusion could be started. So yeah, this is the reason why we first had galaxies and then stars. Now, this stellar epoch spans until present day, though some people say that we're now in the dark energy epoch. It's very relative anyways, but this offers a very intuitive and an easy to understand view of the timescale of the universe. Now that we finished with, I guess, the timescale of the universe, we can go into a little bit about the solar system. And I feel like there's no better way to start than to actually see where we actually are positioned in the universe. So first off, the Milky Way and Andromeda are in what's called the local group of galaxies. They have many satellite galaxies, the small little galaxies there, and they also have this little triangulum galaxy that you can see through a telescope. It's a satellite telescope of Andromeda. But obviously the most significant and by far the biggest are the Milky Way and the Andromeda galaxies. They are sort of dominating this local group. Now that we know about this local group, we can say that our local group is actually part of what is called the Virgo supercluster, which is comprised of approximately 1,500 galaxies. Now you can see each of the other clusters here. It's called a supercluster because it's obviously made out of more clusters. Okay, so after we spoke a little bit about the Virgo supercluster, which is named after the Virgo constellation, of course, we can talk a little bit about where exactly is this Virgo supercluster. And now we got into this very interesting formation of stars called Laniakea. This Laniakea supercluster was discovered very recently in September of 2014, and it has approximately 100,000 galaxies, and it spans 52 million light years, which is huge. You can see that here you can find the Virgo supercluster, and it's definitely one of the biggest structures that we know in the universe. This comes from an Hawaiian word because it was discovered at the University of Hawaii, I believe. Then this Laniakea supercluster, which, as I said, it's one of the biggest, I guess, formation of stars that we know. This Laniakea supercluster is actually part of something bigger. The Laniakea supercluster is part of what is called the Pisces-Cetus supercluster complex. This is a type of what is called a galaxy filament. A galaxy filament is actually the largest known structures in the universe, and they are comprising what is called the cosmic web. The cosmic web, it's sort of like, if you look online like pictures of the universe, you can see that it looks a lot like a spider web. And this spider web is just many superclusters, like these things here, that are actually comprised of many galaxies. So that's the whole thing. But it's actually crazy how big it is. It has a radius of approximately 1 billion light years. And in the universe, it's said that there might be 20 to 75 million filaments. We are part of the Pisces Theta supercluster complex, this one in this diagram here. And it's you have to remember that it's the biggest structure ever known, these galaxy filaments, forming the cosmic web. Next, that we talk a little bit about where exactly we lie in the universe and what is our position relative to, I guess, other things. We can talk about how the Milky Way actually formed. So as I stated before, the Milky Way formed just as every galaxy did. What is the most interesting about it is that it's a very old galaxy. It formed 13.6 billion years ago. So it formed definitely a short period of time after the universe formed. And it basically formed from irregularities in the gas placed almost uniformly in the universe. So since gas wasn't placed that uniform, there started to small irregularities in the gas, small piles, I guess, started to form, and they started to attract themselves gravitationally. They started to orbit around one another, and because of these gravitational interaction, I guess mostly gravity was at play, they started to rotate around a common center of mass, and due to rotation and accretion, gas and dust started to fall more and more into the plane of the galaxy. And after it started to sort of spin and rotate faster and faster, we started to form this bulge at the middle. This bulge is nothing more than a supermassive black hole. And this is the reason why you can look at pictures of literally any, I guess, galaxies online, and you would see that in the center of each galaxy, there is a supermassive black hole. Because it is in the nature of, I guess, how the gravitational field works and how the gravitational force works, that in the middle of every stable object, there is the most massive thing. Just like in the solar system, the sun, which is by far the most massive object, is in the middle of the solar system. In Milky Way and other galaxies, the most massive things are obviously in the center. So in the center of our galaxy, there is a very massive black hole. And at the other parts, there are things that are orbiting around this galaxy. And this is how the Milky Way formed over a long period of time, because it took time for things to cool down and sort of become more and more stable. Now that we talked a bit about the Milky Way, we can talk about how our sun and our solar system formed, though it formed quite in the same manner. So our solar system formed about 4.6 billion years ago. And it still has around, the sun still has around 5 billion years to go. So we're definitely in like the middle part of like the time scale of the solar system. And it's theorized that the solar system formed after the supernova explosion of a star that was many times more massive than our sun. And after the supernova explosion, it left behind like lots and lots of gas. And this gas started to orbit, started to form piles, and then gravity started to be in control. And it started to form these piles of matter that started to attract each other. Like you can think of like small little piles distributed on the area. And some piles merged and formed even a bigger pile. And other smaller piles started to orbit around the bigger pile. And you can also remember that it formed at extreme temperatures, but it started to cool over time. And as the solar system got more and more stable, the star and the planets started to go into a state of what is called hydrostatic equilibrium. So over time, everything started to get into a more equilibrium, into a more, I guess, into a state of equilibrium. And the biggest pile that is in the center of our solar system, as you guessed it, it's obviously the sun. In fact, the sun has 99.86% of the mass of the solar system, which is huge. It definitely dominates when we're talking about the sun. And the rest of the objects are planets. Obviously, the first 4 planets, Mercury, Venus, Mars, and Earth, are made out of rock because rock and other heavier elements were floating closer to the sun. But the last 4 planets, like Uranus, Neptune, Jupiter, and Saturn, were formed farther away from the sun due to the fact that gases like hydrogen and helium were floating like farther away from the sun, and this is why they're called gas giants, and they're made out of gas, while the first 4 planets are made out of rock. Of course, 100 million years ago, you all probably know that the moon was formed due to the collision of Theia, an object that was, I think, the size of Mars, that collided with our Earth and formed our moon. Now, in order to understand why the sun will die one day, we have to understand the mechanism behind the star. So a star is basically in some kind of balance, the balance between gravity and radiation pressure. Obviously, because the sun and each star has a very great mass, this mass sort of pushes, and gravity sort of pushes on the star and is trying to compress it even more. But sun and other stars have a process that is called nuclear fusion. This nuclear fusion works by atoms that merge to create heavier elements, losing mass and creating energy in the process. After the well-known and very famous equation E equals mc squared. You probably heard about this equation. It's very famous and it's very useful because in the center of the sun, we must not understand the sun as like a ball of fire that just burns, because the sun does not burn. The sun, because of its hydrogen and helium supplies, can merge atoms and create other new elements up until iron, but the sun will not create iron. So we can create even heavier and heavier elements after the first 2 gases, hydrogen and helium. And energy, while the sun loses mass because the hydrogen is converted into other types of elements, it gains energy through this process. And it's gained exactly according to this equation here, E equals mc squared. And this nuclear fusion, it's not useful just because it gives us heat and it makes the sun shine very nicely. No, it's useful because this nuclear fusion creates also a sort of radiation pressure here. And this radiation pressure here creates a force that balances out gravity. So the sun, as long as it still has hydrogen and helium and elements to fuse, it will be in a very nice balance. But over time, as it starts to have less and less elements like hydrogen and helium, it will start to run out of fuel to, I guess, fuse and to fuse other elements. So it goes into a state of red giant where its nuclei would get hotter and hotter, while its outside will have a cooler temperature. And the star would have overall a very smaller temperature, but it will have a bigger radius, so it will have a bigger volume. And in astronomy, stars that are cooler are red stars, while bigger stars are obviously called giants, so it will go into a state what is called a red giant towards the end of his life. And you have to understand that this red giant star is very how could I say, dissipated into space. It's not very well knit. It's very all over the place. So the forces are not that strong acting on it. So after the gravity will start to compress it and compress it even more, the nuclei will start to collapse on itself. And it's a very weird type of explosion called a planetary nebula, but that one doesn't compare to a supernova, for example. And it will start to shed out its outer layers. And it will throw away its outer layers, these layers of gas here, into space, creating what is called a planetary nebula, like this beautiful gas here. And in the center, it will remain just a little star called a white dwarf, which is the nucleus of the X red giant here. It's like its nucleus inside. And so the sun will technically become a white dwarf, which has only a fraction of its mass, radius, and temperature. So basically the time scale of the sun is medium star, red giant, planetary nebula, and then a white dwarf. This is the reason why in most planetary nebulas, apart from the background stars, you can see a small little white dot in the center, which is the white dwarf or the nucleus or the nuclei of the former star. This is an example of a planetary nebula, and this is another famous planetary nebula. They are very beautiful. Now, I just wanted to mention very quickly, we're not going to go into many details about the different ways that a star's life can end, but we have to understand that the stellar life cycle, or the death of a star, depends on its mass. So if you're probably wondering the question, okay, will the sun ever become a black hole? This is simply not the case, because only more massive stars with masses greater than n8 masses of the sun will have not necessarily more interesting, but different deaths. For example, it will go into supernovas, which are definitely much more energetic than nebula explosions. Then it will get into black hole. Then you can have a black hole or a neutron star, pulsars, X-ray emission, and other types of interesting things. But with low mass stars or medium stars like our sun, we can have red giants, planetary nebulas, and then white dwarfs. So at the question, will the sun become a black hole? The answer is no, because the sun is not massive enough to become a black hole, which is a good thing because we wouldn't want, I guess, the sun to become too big so that it will swallow Earth's orbit. But yeah, you have to understand that the life cycle of a star depends on its mass. So the more mass of the star, the more energetic things happen, I guess. But that is not the case of the sun. This is the life cycle of the sun. Low mass star, red giant, planetary nebula, and white dwarf. Now, as we got to the closer and closer to the end of the presentation, we're going to talk about 4 theories regarding the end of the universe. How will our universe end? What are the theories supporting it? And okay, how can we know? What is, I guess, the theoretical model that we use to determine the end of the universe, or I guess the fate of the universe? First off, I want to clear a little bit of misconceptions regarding the expansion of the universe. So the universe does not expand like, I don't know, the universe, you don't have to think of the expansion of the universe like this, because we're not expanding. My laptop is not expanding, Earth is not expanding. The only thing that is expanding because of the expansion of the universe that we do not really know what is causing it is that this is the universe itself and the space-time fabric, I guess. But the size of the objects stay the same. The size of galaxies stay the same. So galaxies in themselves do not really change size. Our sun is not getting bigger. This analogy, which I think is great and I really like it, it's this balloon analogy, which sort of shows that, okay, while the distance between the coins, the relative distance between coins changes, the size of the coins does not change. So the sizes stay the same, but only the distances change because the universe is expanding itself. That's the reason why. And this also causes a thing called cosmological redshift, because just in the same way that the space is just in the same way as space is expanding itself, because the electromagnetic waves and light is a type of wave that expands, and its medium is the universe, I guess, the space-time fabric. It expands with the expansion of the universe, and this is what causes redshift. As you can see, I guess a blue wave or just any wave which has a shorter wavelength, it's going to get stretched like an elastic band, and it will get stretched towards longer wavelengths, which actually point more towards the red spectrum. So this is what causes the redshift. All of the electromagnetic waves are getting stretched and going more towards the red part of the electromagnetic spectrum of light. now that we understood how exactly the expansion works, okay, what determines the expansion? Now, in cosmological models, especially the lambda CDM model, which is modeled after the dark energy accelerated expansion, the constant K, which actually describes the curvature of the universe, determines the end of the universe. Now, this is just a purely mathematical model about this constant, and you can see that this K corresponds to a different shape. In the case of a positive K, we can talk that we have a closed or bound universe, and our total energy is negative. This just means that we have a closed or bound universe, just like in orbits, when we have a negative energy, it just means that we are bound to a specific object. We are gravitationally bound. In case of this is a spherical type of geometry. Now, in case of this type of geometry, which is called a hyperbolic geometry, which is shaped kind of like a saddle, the K is negative, so the curvature is negative, and we have an open or unbound universe. And if K is equal to 0, so we say that the curvature is 0, we are living in what is called a flat universe, just like a sheet of paper. Now, you might be thinking, okay, but like, what does math and geometry models have to do with the end of the universe? And the thing is that they are very interconnected. So, as you can see here, the shape of the universe, the geometrical shape of the universe, points towards the fate of the universe. We'll talk just in a few seconds what these theories represent. So, in an open universe that had this hyperbolic / saddle-like shape, expansion continues, but it continues with an accelerating rate, like this red line here. And this accelerated rate would lead to what is called the Big Rip theory. In a closed universe that has this spherical shape, the expansion will stop, and the expansion will stop at one point of maximum expansion, and then it will reverse. So the universe will start to shrink, kind of like the opposite of what it's done until now. And in a flat universe, the expansion is slowed, but it only stops when the time approaches infinite, and it is infinitely dispersed. We will see just in a few seconds that it's the Big Freeze theory. The difference between an open and a flat universe is that in an open universe, we have an accelerated rate of expansion. Also, I'd like to add that the current observations are pointing towards that we are living in a flat universe. So scientists say that K is approximately 0. But the thing is that we are not entirely sure if this is just locally, so if we can only measure like what is happening around us, or if this is the case for the entire universe, because living in a non-Euclidean geometry definitely has its implications, but we're currently not sure about what happens on like larger scales. We can only, I guess, determine what happens around us. Okay, now we're going to go through each theories here: Big Rip, Big Crunch, and Big Freeze. Now, as I stated, in an open universe, so this saddle-like shape, we'll have an expansion that continues, but it continues accelerating, so it goes to a higher and higher rate. Now, this higher and higher rate means that after a period of time, this accelerating expansion can get so accelerated that it can start to break in half atoms. And if this can happen, then this is not okay. This will obviously lead to the death of the universe. And it obviously means that the dark energy has actually won the battle against gravity. So the gravity cannot compress anymore, and dark energy will just like start to expand and expand more things. And this is, I guess, the model. So as you can see, the universe starts to accelerate and it leads to a big rip. So the Milky Way is going to rip, the solar system is going to rip, the Earth is going to explode, and then even the atoms will be ripped apart. And this will be, I guess, the end of the universe. But fortunately, the current value of the Hubble constant does not allow this. The Hubble constant is a constant that actually describes the rate of expansion of the universe. And it is currently too small for it to point towards any, I guess, big rip or atoms even breaking. So this is corresponding to an open universe. In a closed universe, we are talking about Big Crunch, in which gravity actually wins against dark energy. So our universe, which is currently expanding, we will only expand up until a state of maximum expansion. And then its expansion will actually start to reverse, and instead of expanding, it will start to compress into a singularity, much like the one it started with. This is what happens in a closed universe. So expansion doesn't continue forever, and the matter and the particles will be reunited back into a super dense state, a singularity, as the one that we began with, just as the Big Bang. But instead of the Big Bang, we have a big crunch. Now you can see that, okay, this poses an interesting question, but like, what if this happens over a longer period of time? So we have a cycle of big bangs and big crunches, big bangs and big crunches. Well, this is a particular case of the big crunch theory called the big bounce theory. And it proposes a symmetry of time, that the universe is in a continuous cycle of big bangs, states of maximum expansion, then compressions, and big crunches, and so on and so forth, going from a state of singularity, expanding, then reversing its expansion, and going through another state and another singularity. This basically proposes that the same events took place trillions of years ago into multiple iterations. So this is very interesting if you think about it, the fact that we might have had the same conversation a trillion years ago. So this is the particular case of the Big Crunch theory called the Big Bounce theory. Now, the last theory, which for now scientists think that is the most plausible one because it points towards a flat universe, which, as I said before, we kind of measured, though we're not entirely sure, which is called the Big Freeze theory. Now, this Big Freeze theory is quite interesting because it points toward a heat, it's also called the heat death of the universe. So it points toward a more, I guess, thermodynamic approach to the universe. It treats universe as a very big thermodynamic system. So in the Big Freeze theory, it just states that nor the gravity nor the dark energy will win their battle, and they will sort of be equal to one another. So it basically states that our universe will go through a state of thermodynamic equilibrium. This, by the way, this theory actually, as I stated before, comes from the second law of thermodynamics, which states that in an isolated system, entropy tends to increase. The universe will get through a state of maximum entropy, while all energy is evenly distributed and no further energy transfer can occur. Now, what does this state of maximum entropy mean? You do not need to know what exactly entropy is. It's just a measure of order or disorder in the universe, but a maximum entropy means equilibrium, and this equilibrium means that nothing can happen anymore. There is no way to measure time, distance, or direction, and all things will cease to have any useful meaning. Because if given sufficient time, starting from the second law of thermodynamics, physicists say that the universe will asymptotically approach a state where all energy is evenly distributed. And if all energy is evenly distributed, as no further energy can occur, nothing can happen anymore. As I said, we cannot measure time, we cannot do anything, because obviously the energy is evenly distributed. So the temperature will drop and tend towards an absolute zero. This absolute zero value means that there will be no kinetic energy of molecules or like vibration of molecules. So molecules will stop doing anything. They will sort of be frozen in time. There will be no energy. So this is a very sad theory because from a very lively universe full of energy, full of light, we will get to a frozen, dead universe. Also, all stars will die, and there will be only brown, black dwarfs, or black holes that essentially are do not require any further energy transfer. And yeah, this state of maximum entropy just states a frozen state of time of a universe. Sorry. So this is why it's called Big Freeze. The universe will just be frozen and no energy can occur. The molecules cannot move anymore. And this is, I guess, at least for now, the most plausible model regarding the end of the universe. But we are also waiting for, I guess, new and more data, more and more theories to develop, because, as I stated before, we're not entirely sure about about the measurements of these parameters. And yeah, no new theories are coming out very often. Also, these are the most well-known theories and the ones that are mostly supported. There are also very interesting theories like the string theory that unfortunately are not that that are very controversial and that are not not necessarily appreciated, but many scientists do not believe in them because they are a little bit too complicated mathematically and probably do not really make any sense, or they just do not have any experimental data to support them. But this model of the universe, especially the Big Bang model and the current cosmological model, is the one that has the most experimental data. Though there are many things that are currently, I guess, in the dark and we perhaps do not really know much about them, we will see how it evolves over time. This is a little synthesis of what we talked today. So this is the model of expansion. It's basically asking, okay, this expansion, will it stop? Will it stop when the time is infinite? Will it accelerate? Or will it actually just reverse itself and start compressing? These are the theories that we discussed: the Big Rip, the Big Freeze, and the Big Crunch. And this is our, I guess, the 4 models. Now, I decided to end this presentation with a quote by Isaac Newton because I feel like it perfectly sums up what we talked about today, because this area of cosmology and astrophysics is has currently many new theories, and it is currently under construction since there are many things that we do not know about, and perhaps there are things that we will never know. And it's definitely an area of physics and astronomy that is very, I guess, that has very questions. It's not that well understood, and there is not many experimental data, and it mostly just is in the area of theoretical physics. There are mostly theories. And since there will be perhaps things that we can never know, and we obviously do not know that much right now, we've since made a long progress since the things that we talked in the beginning, the theories that philosophers proposed over the years in the beginning. What we know is a drop, what we don't know is an ocean. Isaac Newton. Thank you very much for paying attention to my presentation, and I would like to, if you have any questions or perhaps you want to talk about the theory that you support the most, then I would really appreciate if you would like to start a debate. Thank you very much for your attention.
Thank you, Andrea. Very interesting presentation. Your quote of Isaac Newton is very similar to the quote of Carl Sagan, who said that we are a very small grain of dust in a vast and endless beach. So it's really, really nice. This shows how incredibly large is the universe. So thank you very much. Audience, do you have any questions? We have a few questions in the chat. Let me open the chat. What was the universe before Planck time? That's a €1 billion question. We could have received a Nobel Prize for that, actually, if we knew what happened before the Big Bang and before the Planck time. But we have someone with us who is doing some experiments related to the early stages of the Big Bang. Yannis?
Yorgo, tell me.
Yes.
There are some questions here that what is smaller than Planck time? And I said that's a €1 billion question, and if we knew for sure that we would have won the Nobel Prize by now.
We don't know about that.
Yes, that's my answer. And I said that you are doing some experiments related to that time.
We do about hadrons emitted in the before the freeze out stage. Some leptons or virtual photons that they come out from the primordial universe, but we don't have a specific answer to Planck constant for the specific question.
Alfred, does this answer your question? Yes. I guess.
Okay, thank you. Thank you very much.
You're welcome. Any questions? Any more questions?
I think someone asked about bibliography or what are the best resources for learning more about the history of the universe. And I personally really like perhaps science videos on YouTube. There are many dedicated channels that ask these questions. And also Wikipedia.
From trusted sources, not conspiracy theory.
No, trusted sources. Also, sometimes Wikipedia can be a pretty good resource because it can actually link some certain articles that you can then be redirected to, and I thought that was very useful. And also, there are many books that I like. I feel like a book that I read and that I liked that tackled this question is Astrophysics in a Hurry by Neil deGrasse Tyson. And this is also, there are also like many introductory books that are more for, I guess, popularizing science. But I heard that there are some great books by physicists that are great to understand even for, I guess, school level presentations. In my case, for example, Black Holes and Time Warps by Kip Thorne, who I think worked with Stephen Hawking on developing like the theories regarding the gravitational wave model, is a great book, and I've heard positive reviews about it, though I haven't really been able to look into it that much. But yeah, I feel like especially online, there are many like physics courses that I used a lot when researching for my presentation, and I really like looking on physics courses from different universities. That is my sort of what I used to gather this presentation. I saw that someone also asked what causes the big freeze. Well, it's not caused by something, it's more, I guess, of a process, but it's mostly caused, or this theory is actually, as I said, it starts from the second law of thermodynamics. This law stated that in an isolated system, entropy tends to increase. So a thermodynamic system is like, I don't know, can be anything from your refrigerator to, I guess, when you're cooking lunch in a pot and you're increasing the temperature and the molecules are vibrating so you can make soup or other types of food. Just like we treat these as thermodynamic systems, we can treat the universe as, I guess, the biggest thermodynamic system. And starting from this second law of thermodynamics, people stated that, okay, if we can apply this law to thermodynamic systems, we can also apply it to our universe. And applying it to our universe leads to this thing, that the entropy will increase, and it will increase to a maximum level. So this maximum level will basically mean equilibrium, and the temperature will sort of start to drop, because you can see that it is a trend for the average temperature in the universe to increase. Also, you have to think about how you don't have to think about things locally. Like, yes, the universe is the earth is getting warmer and the sun is giving us more energy, but we're talking about the universe as a whole, so not other like isolated systems. And at the same time, as the temperature starts to go smaller and smaller, it will approach a zero, and this zero value can lead to molecules no longer vibrating and just staying frozen in time. This is essentially what entropy means, and this model is also very heavily based on thermodynamic laws. Thank you very much for the kind feedback. I really appreciate it, and I hope you all enjoyed the presentation. If there are any more questions that you would perhaps like to ask, then I'd be more than happy to answer them. I think you're on mute.
Oh, thank you, Chris, for letting me know. So I said that let me repeat then what I said. I said that yes, of course, congratulations to Andrea. She did it perfectly, and if you remember, as I mentioned in my email for the presentation, use simple words, and it's a difficult subject that we are going to deliver, and you did it perfectly. Congratulations again. And of course, she's excellent. She's very comfortable with her subjects and her knowledge, and she gave us a great talk. And you can go online and see her resume. She did a lot actually in this young age, and she's done her own scientific publication, which I will love to spend some time and read it. And the next time you can prepare a presentation for us on your publication, scientific publication, Andrea. Just feel free to do it. You can do it in May, you can do it in June. Let us know. And it's an excellent opportunity for us to meet you and have you with us. Feel free. You can also join our online science Café anytime, but also join our research. We can share with you online the screen, and you can join our research. Now, thank you again. And now, guys, as far as the Global Astronomy Month that I mentioned earlier, the KITION Planetarium Observatory with the director George Troullias, me, I'm the national coordinator for CYPRUS, and I'm also part of the international committee. We are going to celebrate this April the Global Astronomy Month. This Global Astronomy Month was inspired by the 100 hours of astronomy, which were introduced at the International Year of Astronomy in the year 2009. After that, we had the establishment of the Astronomy Without Borders Society, and we have the motto "One People, One Sky," and the point is to unite all the people to share knowledge all over the world, share observations, and we do astronomy for inclusion. We do astronomy without racism, and we try to include everybody in our projects, no matter the level of knowledge, no matter the status of the citizens, and no matter of if someone is disabled or no. So we do also have some projects for astronomy for disabilities, astronomy for autism, for the hearing impaired, for the visually impaired, for Down syndrome. So we want to share astronomy and knowledge with everyone. So during April, we have it's a month full of activities worldwide. It's one of the biggest events worldwide, and I will start with the Global Star Party because everybody likes star parties. Usually we do it at the end of the month. It's closing down event. This month will be on the this time will be on the 26th of April, and we will do everywhere on the world. We're going to have in every country, we're going to have a star party where we are going to have a theme for that party, either messy marathons or observations of some sky objects, and then a small talk and observations with telescopes and sharing stories about space, about the moon, etc., from different countries, from different tribes. We will have the Sunday. Usually the Sunday is held on a Sunday to celebrate the Sun Day. So the proposed date is Sunday, the 7th of April, but this year we proposed any Sunday during the month. So usually we do it in the morning time, around after 10 o'clock, 11 o'clock. We gather people, we show them the sun with UV blocking filters and hydrogen alpha filters, so they can observe the solar disk, the photosphere and the heliosphere, and they can observe the prominences of the dark spots, the sunspots. And then we have some live online sky tours by our friend Gianluca Mazzi in Italy from the Virtual Telescope Project, Bellatrix Observatory. And we have a very, very important event on one of the longest duration of total solar eclipses for many years now. It's going to take place on April the 8th, and we're going to broadcast it. We have the asteroid search campaigns in cooperation with NASA and Hutchinson University in Hawaii. We have some observational challenges. We have the Globe at Night, where we promote ways to save the night sky from light pollution. And we also celebrate International Dark Sky Week during this month. Dark Sky Week starts on the 2nd of April and lasts until 8th of April. And we're going to have some projects, and we're going to take some measurements of the light pollutions using some charts of constellations. We will upload some April sky maps for the Northern Hemisphere. And also we have the cultural event, which is the poetry and the visual arts and the kids astro art projects. Anyone could do a drawing, a painting, and send it to us, and we will include it in the international competition. And of course, 15th of April, we have the first quarter of the moon, where we observe near the terminator to observe for any meteorites, any flashes, and also it's better contrast on the lunar surface, and there's no too much illumination to destroy the vision, to get the eye tired, like we have, for example, during the when we have full moon. So it's better to observe when we have quarter moon. Digital painting is also accepted. Why not? Let's try it, Hasret. Why not? And so we're going to have a few meetings online as well, international meetings. So keep in touch, follow the schedule, follow our website, astronomycyprus.eu, and also please follow our KPO Cyprus at Instagram and our Facebook page now, KITION Planetarium Observatory. We will prompt everything there, and also on the YouTube channel under my name, Troullias, we will be posting some things. Usually we do some fun science there, making fun of those that we believe that the Earth is flat, and we are explaining it with some examples. So please feel free to contact us at any time if you are interested for any event, or if you want to make your own talk during our science cafes. Thank you very much, everyone. Anyone wants to say anything? Yes, Hasred, you can find this explanation at the website and on the newsletter. But if you visit the newsletter, we have all the links on the newsletter. I will post it here now so that you can follow the link on the newsletter. If you go to the astronomycyprus.eu home newsletter, and you will find the latest newsletter, volume 17, version 3. I'm posting it here. Well, thank you once again for joining us. Next month, last Tuesday of next month, same time, we will be here 8 o'clock. Just have in mind to add the extra time for those that they have daylight saving.